Hi everyone. I'm going to talk about cyclic voltammograms and how we can simulate them, and that we need kinetics to converge experiment and theory, which I will show for the copper-aqueous interface in alkaline conditions. Let me briefly start off by introducing cyclic voltammetry, or CV. In this very fundamental electrochemical technique, we vary the applied potential shown here on the x-axis in a cyclic fashion, whereby we iteratively apply cathodic and anodic sweeps. We record the current density response, which gives us features and peaks characterizing our electrochemical system. Shown is here the example of platinum 111, where going from negative to positive potentials, we obtain hydrogen under potential deposition, double layer charging of the clean platinum surface, hydroxide absorption, and at very positive potential platinum oxidation. So as you can see, we really can see every electrochemical process occurring in our system. Modulating the sweep rate, for example, so the change of potential of time, we even get information about kinetic and mass transport limitations in our system.
However, while we do see everything in the form of a current response, we usually don't know a priori what electrochemical process each feature corresponds to. For this, we either need complex analytical tools or computational approaches.
And such simulations of CVs are usually based on a thermodynamic approach. And here we simulate electrochemical reactions or adsorption processes individually, for example, of a species A+, adsorbing while simultaneously consuming an electron. And we can express this current response by an expression where we expand the current density, which includes the sweep rate, the change in surface coverage of our adsorbate with potential, the amount of consumed electrons in the adsorption process, and an area normalization. The central property here is the change in surface coverage with potential, and that is something we get, for example, from standard phase diagrams or Pobet diagrams, where we plot the stability of our surface states versus potential. Shown here is then an example of such a diagram where the lowest lying state corresponds to our predominant surface state. For example, at negative potentials, we have an adsorbate A. In the middle, we have a clean surface, and at positive potentials, we have a oxidatively adsorbing species B predominant on the surface. Differentiating the stability diagram, we will obtain something resembling the surface coverage, the surface charge versus potential, including the negative charge, a neutral surface, and a positive charge. The second differentiation with time will then give us basically the change in charge with time, which is nothing else than the current density, something which we get in ACV. I noted before that the central property is the change in surface coverage with potential, and that is what we obtain via ab initio simulations or quite readily via DFT. Of course, the accuracy of these simulations or the predictive quality then depends on the chosen underlying electrochemical system. For example, what solvent do we apply, an explicit or an implicit one? How deep we apply a configurational sampling to describe the surface coverage of an adsorbate, here, for example, in hydroxyl, and how we model the potential dependence of our adsorption processes. For example, we can use the computational hydrogen electrode or include more detail with its generalized variant.
We can extend the thermodynamic picture by including mean field kinetics. In that sense, we add electrochemical reactions to describe Faradaic processes and go beyond the electrochemical adsorption of a species. For example, our species A+ can now adsorb and even further get reduced to a species B, which finally gets released as a species BH. In that sense, we still describe our CV signal by including the pseudocapacitive processes on a basis of the description in the change in coverage with potential, but we further include the Faraday currents, which are described by the forward and backward rates of our Faraday processes, usually simplified via what's happening around the rate determining step. In that, we also include the number of electrons consumed in our Faraday processes in a continuous fashion. As opposed to the thermodynamic approach, we now do not obtain our coverage potential relationship from a phase diagram derived from DFT, but we directly use the coverage obtained from the steady-state connections. We note that in order to include the kinetics properly, we require electrochemical barriers. These can be approximated through DFT, or if enough information is available, we can fit them to experiment.
Now I'm going to talk about the application of simulating CVs and specifically about copper single crystals in alkaline conditions. And this is motivated by the work of our collaborators who found that you can obtain very clean CVs by avoiding contaminations of glass and air, which previously always led to feature-rich CVs, and when avoided, yield very clean signals.
These very clean CVs present an excellent opportunity to compare to simulated CVs. As shown in the top panel, we do this for 3 different single crystals, namely copper 110, copper 100, and copper 111, which we compare within the potential window in which we expect hydroxide adsorption. We start with the thermodynamic approach where we include the expected adsorption of hydroxide and protons from water according to alkaline conditions, and we include a rigorous sampling of the surface coverage for the different facets. Further, we neglect CA oxidation as this is not our object of focus. The simulated CVs look rather different than what we expect. First of all, we find in some of them 2 signals instead of 1 signal, and the area under the peaks is larger than what we find in the experimental spectra.
Since we perform simulations, we can relate these features to the specific adsorbates as shown in the bottom panel. And here we see that the peaks located at the more positive potential correspond to the OH adsorption, whereas the peaks at the more negative potentials correspond to hydrogen adsorption. In the case of the 110 crystal, these peaks even overlap, explaining this very large charge associated with it. Now, what we can see from this is that we possibly overestimate the hydrogen adsorption, and that is due to the fact that we ignore the hydrogen evolution reaction, or HER, where we expect that adsorbed hydrogen is continuously further reduced to form hydrogen gas. And this is what we're going to include in the next step. Here we again include our surface coverage dependent terms, and as well as the full kinetics based on barriers which we fit from experiment, which were recorded by our collaborators. The kinetic model we solve using a cat map.
Now including the HER current, unsurprisingly, the hydrogen adsorption peak disappears and gets replaced by the hydrogen evolution current. We now dare to make some quantitative comparison. The first one is the adsorbed charge based on our hydroxyl peaks, which is nothing else than the area under the curve where we compare now our experiment and theory. And as shown in the table on the bottom taken from our publication, we actually get extremely good agreement for copper 111 and 100, and an agreement with copper 110, which points though to a 1/2 reconstruction. What has less good agreement are the hydroxide adsorption peaks, where a deviation between the adsorption signals is between 100 and 200 millivolts. While this lies within the typical DFT error, we can, however, still improve on this deviation by incorporating more accurate salvation energies, which we can take as a posterior correction from AMD. Now we are able to obtain agreement within 100 millivolts. And with that, I'm going to summarize and conclude my talk. I hope I've shown you that simulating CVs is very useful to understand what's going on the electrocatalyst surface. I hopefully have convinced you that we can become quite quantitative when having very clean experiments and carefully conducted simulations. And finally, I want to thanks to our funding partners, our group at CAT Theory at DTU, our experimental collaborators at DTU, and you for listening.